Alright, welcome to AP video 10.2, looking at determining the type of IMFs. Main objectives here are to use Lewis structures and their polarity to then be able to determine what kind of IMF will occur. Make sure you turn off your distractions, pause your mind as you need to, and take some extra notes in the margins. Here we go. Alright, so to try to figure out what kind of IMF is going to take place in a molecule, or between molecules, because intermolecular force, it starts with molecular polarity. So recall from last chapter that a molecule is polar if it's asymmetrical, and nonpolar molecules have symmetrical distribution of the electrons. Here are some electrostatic maps that show electron distribution in atoms. Basically, the more red you have, it means there's lots of electron density, and the more blue it means there's little electron density. So when you look at these are molecules that are already drawn three-dimensionally, and they just kind of color code them as well. So here you can see we have the shape of trigonal pyramidal. There's technically a lone pair of electrons here, on the top here, and that's why it's electron dense up there. So this is a polar molecule. When you look at this one, it's very symmetrical. Notice how the red and everything is being pulled in all directions kind of equally like this, and all those basically cancel each other out, and this symmetrical distribution is nonpolar. Here in HCl, lots of electron density here, so this one's going to be a polar molecule. Here's water in a bent shape, and remember water's got those lone pairs over here, so that's why it's high electron density here. It's a polar molecule. Here's H2S, also polar, asymmetrical. Here's carbon dioxide, very symmetrical. It's got polar sides, excuse me, it's got negative sides, but they're equally negative sides, so therefore it's a nonpolar. Same with this diatomic molecule, nonpolar. Here's HF, which is asymmetrical and polar. And this one is also, this one is nonpolar because it's tetrahedral, and it's symmetrical and tetrahedral with all its 4 carbons being pulled out. So symmetry helps you figure out the polarity of a molecule. So I got this poster here in the classroom, and basically these can be any molecule, those little blue dots there. So all IMFs are experiencing, all molecules are experiencing IMFs in all directions, maybe even with the molecules in the glass container they're in, but they're experiencing IMFs. And basically these things can be strong or weak, and remember we have London dispersion forces, which are the weakest force of attraction. So if these were LDFs here, they'd be weaker forces of attraction. Then we have dipole-dipole, it's a little bit stronger, and we have our hydrogen bonding, which is the strongest. Okay, so we're going to try to figure out which type is occurring by drawing our structures out. So what you need to do here is draw these out, and you need to go through your Lewis structure and try to draw those. So I'd recommend you guys pause right now and try drawing these, and then we'll kind of analyze them when you're done drawing them. Go. Okay, so you should have drawn these out now. So we have this one, which is CH2Cl2, and it looks something kind of like this. And there's lone pairs on those. And basically that's your molecule. So this is actually tetrahedral. I'll just put tetra here. And tetrahedral would have these things kind of going off like this. And it's asymmetrical. The outside atoms are kind of asymmetrically distributed here. And that's our molecule. And because it's asymmetrical, this will be a polar molecule. Now, to determine the type of force, whether it's LDF, dipole-dipole, or hydrogen bonding, is you have to figure out what's going to happen. So the second two here, this is when you have polar molecules. And now we have to decide, is it dipole-dipole or really strong hydrogen bonding taking place between these molecules. So this little picture here again is trying to just represent any kind of molecule. What kind of IMF is taking place? Well, in this molecule here, this one is just a regular polar molecule. We have carbon bonded to chlorine and hydrogen. We don't have that situation of hydrogen bonded to oxygen, nitrogen, or fluorine, so it's not superpolar, so therefore it's just going to be a dipole-dipole. So the type here is dipole-dipole. In your next one we have ClF4, and it looks something like this, and for the sake of time here I'm going to leave off the electrons, but there's a lone pair of electrons like this on all the chlorines. This molecule is completely symmetrical, and therefore symmetrical means it's going to be nonpolar, and nonpolar is always going to be the LDF. So this is a nonpolar molecule, and your only force of attraction for nonpolar is LDF. For your last one, remember when you have CH3, it means the 3 hydrogens are on that carbon, and the carbon is bonded to the next thing, which is oxygen, which is then bonded to another hydrogen. And then don't forget oxygen needs its lone pairs, like this. So there's your substance. And right here, whenever hydrogen is bonded directly to oxygen, that's not the hydrogen bond, by the way, but that creates a very polar part in the molecule, like extremely partial negative and extremely partial positive here. So therefore, the IMF that's occurring between, if this molecule is this one right here and this one right there, their intermolecular force is that it's unusually strong, and we call that the hydrogen bonding taking place there. So this is a polar molecule, and inside of it, hydrogen is bonded directly to oxygen here, and that creates that very strong dipole in the molecule like this, and therefore the intermolecular force is going to be H bonding, hydrogen bonding. Alright, so it's a little bit of practice with that. Woo, whoa, whoa. Okay, so on this last part here, I'd like you to kind of practice one as well on your own, and then we'll kind of use it to springboard our class discussion. We'll do the first two together. So you want to check if IMFs are occurring, and then also circle which one is the most dominant. So one thing you need to know is if hydrogen bonding is occurring, that technically means dipole-dipole is happening, and if you have electrons moving, you always have LDF. So basically, if you check the last one, technically they all have to be checked because LDFs is the movement of electrons creating random polarizable molecules, and that's always happening if you have electrons. So every molecule has LDF, so I guess you can all do that really quick. Okay, and then dipole-dipole might happen and not H bonding, but if H bonding is happening, dipole-dipole is because H bonding is a type of dipole-dipole. So if we do the first one together, CH4, you would draw this, and don't forget on all these, you really, when in doubt, you have to draw these out to figure out its polarity. But methane, CH4, looks like this Lewis structure-wise. It's tetrahedral, so it looks like this, and it's completely symmetrical. So therefore, this is a non-polar molecule, and it only experiences LDF, so this is all it's got going on there. So we check that it's happening, and this is the most dominant force, and it's LDF. So next, we'll do NH3. NH3 looks like this, if you draw it out. It's got 4 domains, so it's tetrahedral in terms of its arrangement, and there's a lone pair of electrons up here, and but they don't occupy space. And this molecule here is going to be trigonal pyramidal, and it's asymmetrical, so it's polar. So this is a polar molecule. So it's got LDFs happening, it's polar, so it's definitely dipole-dipole. Now the next question is, would this molecule, if it came next to another molecule like itself, so if I'm going to draw 2 of these just kind of like that, when they're next to each other, is this unusually strong IMF there hydrogen bonding? And the answer is yes, because within inside this molecule, hydrogen is bonded directly to nitrogen, which creates a very strong dipole right there, or polar molecule, and these things attract together pretty strong with IMFs there. So this does have hydrogen bonding, and that is the most dominant force there, and we'll circle that one. So what you need to do is draw your molecules and check in the boxes here, and we'll kind of have a little discussion about this. Alright, we'll see you tomorrow.